Hi, everyone. This is the Hungry Math Professor here, and today I'm going to be talking about Russell's paradox, and I'm going to talk about it in the historical context. It's related to some of the videos I've been doing, and it comes up in several of the books that I've discussed on this channel. So I thought it would be good to go through what the paradox is, and then I'm going to do a follow-up video where I show you how Russell's paradox shows up in a surprising way that actually Russell didn't see, even though he pointed out his own paradox to Frege. So first of all, let me just mention that um, it's called Russell's paradox, but has been that I've learned through one of the books that I've mentioned by Ulrich Felgner. Maybe we should call it the um, Russell Zermelo paradox, because it turns out that Zermelo also discovered this problem around the same time. Of course, the world was not as connected as it is now, and so it was possible for people to discover things completely independent of each other at around the same time, and not know for a little bit of time that that was the case. I suspect that maybe we call it Russell's paradox in part because of the episode I'm about to tell you about in history. But in any case, Zermelo also discovered this issue. So that's Ernst Zermelo, who's famous now, in particular for Zermelo-Fraenkel set theory, his name being attached to that, and then Bertrand Russell. Now, if we want to tell this story properly, we have to take a step back from Russell and Zermelo and start with Frege. So Frege um, is a logician, a philosopher, and a mathematician, and he's famous in part, mostly for his development of axiomatic predicate logic. So modern axiomatic predicate logic. And although we probably don't use exactly the same notation, I highly doubt that. We are basically, it was developed by Frege, and now this is, as I understand it, basically what we teach, what I teach my students now, and what's used more formally in the field of mathematical logic. And his big um, introduction here that was really important was to show how to a reasonable way to quantify variables, not only notation, but a way to incorporate it into logic that made a lot of sense. And before that, so it's very famous, or it's very well known that Aristotle was one of the first to like write down laws of logic in some systematic way. And Aristotle's logic um, dealt with, and, or, not, and implication, these very important um, logical devices that we still use today, but didn't have a good way, um, didn't have a good way to handle quantifying variables. I mean, even the way I'm saying that is in the modern language. But anyway, and if you want to look more carefully about what was wrong there, I'll let you look that up. I don't want to get into the weeds here in this video, but so I don't want to get into exactly what the issues were at a very detailed level. But this is the story, and so this is known since the time of, like, this issue was known since Euclid's Elements. So in the sense that there were statements, important statements made in Euclid's Elements to which Aristotle's logic couldn't like completely capture, right? So what's interesting though is like how long it went in the history of things before people, um, before someone sort of made some developments in this. But I suspect that, because Frege is in the 1800s into 1900s, so we're at the turn in mathematics history where we're starting to really want to make things more rigorous. And part of what we're going to need to make things more rigorous is first of all, a more carefully um, designed logic that can be used to ground all this stuff, right? So I think it's partly because of where the math community is going at this time that is driving this to some degree. But Gottlob Frege is the one who makes this big innovation, points to some good notation, but also develops a way of quantifying these variables. Now, there's something else though that Frege is interested in. So this is he's also famous for this view called logicism. So this is Frege's view. And so while he's developing this predicate logic, he also has in mind this goal of showing that his logicism project is um, something that can be carried out. So what is logicism tries to do in simple terms, I've talked about this in other videos, but it's important to this video in particular, is that it tries to show that arithmetic, surprisingly, I think I'm going to misspell arithmetic. So yeah, arithmetic is a branch of logic. Okay, so here, I mean, when we say arithmetic, he's talking about number theory, and he wants to show that it's not just that you can build number theory on top of logic. So you start with logic, then you build axioms for number theory, and then go from there. That's the way we do things now. He's saying instead that you just have to tell me what the laws of logic are, pick, and they'll sort of be these self-evident truths or these grounding axioms for logic, and then arithmetic can just be built from there inside of logic itself. And so he's trying to show that arithmetic is just a byproduct of logic. And that would be a very powerful philosophical position to try to say that math has the same sort of status that logic does. And then he's also he's also a Platonist, so he wants to use this whole project as a way of bolstering his Platonist ideas about the existence of mathematical objects. So this is his whole project that he's working on here. And so the goal here is to lay down the axioms of logic as self-evident truths and show that arithmetic follows. Okay, but in order to do that, you're going to need to, in your logical axioms, you're going to have something beyond what we usually think of modernly as logical axioms. You're going to need some kind of set axioms. Okay, but he's hoping that these set axioms will be basic enough that they'll feel just as self-evident as like the logical rules, right? Okay, so they shouldn't be too like complicated looking, basically, right? So one of these, I mean, I'm not going to show you the exact axioms because that's not completely necessary, but one of them basically in modern language, or the way that I teach this kind of thing, it basically says that you can build sets in set builder notation. This is a little bit simplified, just to be clear, but it's saying that you can build sets in this sort of basic set builder notation, meaning that I can form a set in the following way: the set of all x such that, right, this line stands for such that f is some predicate here that tells me restricts x in some way. So the set of all x that satisfy f of x is a set. Okay, and he's very unrestricted about this, and so it needs to be very unrestricted so that it can feel maybe like it's a self-evident truth, or just as basic as logical rules. Now, if you want to look into this even more carefully, this is going to be related to what's called Frege's basic law 5, okay, which is one of these axioms that he puts down. I don't want to get too much into that detail per se in this video. Maybe I'll do that in another video. But if you want to look even more carefully, that's where you would go. Okay, and it gives you even more details as to how the set builder notation works for Frege. Right now, I'm being a little, um, not as careful about those particular axioms, but basically we have this set builder notation, and we're not very restrictive about what F can be. We're trying to allow it to be, almost anything. So, um, interesting enough, he publishes this paper called "The Foundations of Arithmetic," and this is in 1884. So this is where he develops the logic, and quantifier variables and things like that. And then he starts continuing this development, and he publishes something called the Basic Laws of Arithmetic. This is all translated from German. So he has volume one, and that's 1893. I think in that first volume, he starts to um, introduce his logicist ideas, but doesn't quite flesh it out. And then it's in the second volume, which was published at his own expense, probably because there's not enough people reading this stuff to make money or something like that. But he's committed to his project, so he's making this volume two. And here's where he's going to flesh out his logicist project in detail using his logical notation and things like that. And the story goes that he was basically ready to send this thing off to press. I mean, he basically written it. If you're sending it off to press, it means you've already written it and you've already edited it, right? So you're ready to go. And he receives a letter from Bertrand Russell, right? So this is the crisis moment. So he receives a letter from Bertrand Russell. And this is no mathematician wants to have this experience. I mean, we wouldn't get a letter now, we would get an email, but no one wants to have this experience where you are ready to go on a paper, maybe even post it to archive in more modern terms, and then you get an email, or maybe you've already published it, who knows? And then you get an email from someone, you probably know this person in some way, and they point out a fatal flaw in your work. And it's just a terrible feeling. I've never had that experience, but I've had enough paranoia to worry about these things. So I've had some experience of what that feeling might be like. And then I assume when you're actually in the middle of it, it's just this awful, awful feeling. And in Frege's case, I mean, this whole second volume, I think, was just completely destroyed. That being said, we still, it's funny because even though this is considered a failure now, we learned so much from it, and we developed so much from it. So, when we say failure, we should, it's relative to the fact that we still learn a lot when we fail sometimes. But anyway, let me point out what the issue was that Russell um, pointed out in this letter. So here's the following set that we're going to consider. So we're going to consider the set of all x, and my f, the predicate, is going to be the set of all x, so that x is not an element of itself, right? So with this element of sets, just in case, I'm kind of assuming you understand some things about sets here, but just in case, if we have this set that contains A, B, and C, and this is the set S, then I would say A is an element of S, right? But I would not say that in this case, S is not an element of itself. Okay, because I can't, the whole set S is not contained in this, in itself. Okay, so in any case, this is the element of is a basic, predicate in set theory. There's no real conceivable way to think of set theory without that predicate that I've ever seen. So in any case, this is the set that Russell pointed out, and so oftentimes we call it R for Russell. And here's the issue with this set. First of all, under Frege's development, this set is completely supposedly legitimate. You're supposed to be able to form this set. And so this is why it's a fatal flaw. So now we say, okay, well, the question now is, so here's the question. Is R an element of itself, right? Okay, so now we say, all right, well, let's start with the fact that if R is an element of itself, let's just assume that's the case, then that means by definition of the set that R must not be an element of itself. So we say, okay, well, that doesn't work, right? If R is an element of itself, then R is not an element of itself. So let's try the other way, right? So then if R is not an element of itself, but then by definition of the set, then R is an element of itself. And we have this problem because, again, both assumptions led to the opposite fact, which is a contradiction. So both of these situations lead to a contradiction. And, when he got this letter, when Frege got this letter from Russell, I think he probably realized right away that this was a problem, but I'm sure he also tried to fix it, or I know he tried to fix it for a while. And at some point he does publish the second volume, but he puts some like addendum or some note saying like that there's this issue that Russell pointed out, and Frege tried to fix the problem by amending his basic law 5, and he just couldn't see any way to do it. So it's just kind of this, he puts this little like note of defeat, but he wants to publish his volume anyway. So this alone is not the end of logicism, because actually, as I mentioned in other videos, so after this, Russell and Alfred North Whitehead take up the project of trying to, they also have this sort of, they take up Frege's logicis project to try to develop mathematics as solely coming out of logic. But this also is seen to have failed. And at that time in history, there's a lot of people, including Ernst Zermelo and Russell and Quine and von Neumann and Gödel, and lots of people working on set theory, other people that I'm not going to be able to just rattle them all the names off. But eventually it becomes clear that first order logic is its own separate thing. This is especially because of Gödel's work, that first order logic should be its own separate thing, and has Gödel's completeness theorem for first order logic to sort of one fact that solidifies it as its own sort of thing in some sense. And then on top of that, we place the axioms of set theory. And because they are their own axioms built on top of logic, they are separate in that sense. So it's not a logicist, it's not, at least the Frege's logicism is not the way we develop things. We really see them as separate because the axioms of set theory are placed on top of logic. And that's what we call now the Zermelo-Fraenkel axioms of set theory. And that's how we've learned to develop things now. But this was a crisis when these sort of these paradoxes and antinomies were discovered, and it took a little bit of time for many different mathematicians to work out what we now call Zermelo-Fraenkel set theory, and there were other alternative set theories that are still, some of them are still studied today, that were being developed around the same time. So this is Russell's paradox. And then again, as I mentioned in the beginning of the video, I will make another video on Russell's paradox where I show you how Russell also made his own mistake accidentally in disguise after he had pointed this out to Frege. Okay, thanks for checking this out. Like, comment, and subscribe, and I hope to see you at another video.